Hi Janakiraman.
Hi Annie. So, I thought, having done a lot of problems in superposition, right, using superposition with voltage sources and resistors, I wanted to just pick your brain on this idea of a current source.
Okay.
What is a current source, first of all?
Okay. So, maybe let's review what a voltage source is.
Yes.
And then that will help us understand what a current source is. So, as we have studied, so if you have a voltage source between two nodes A and B, what the if the voltage source's value is V, what this source does, it enforces a potential difference VAB equal to V at all times.
At all times?
At all times, irrespective of anything else. VA is going to be higher than VB by a voltage V.
For any current that is coming out of that?
For any current that is coming out of this source. In fact, it doesn't matter whether current is entering or current is leaving. And the magnitude of the current doesn't matter. Conceptually, you have an ideal voltage source V, which maintains a potential VAB equal to V.
Okay, so I think this is sort of easy to relate because our mobile phones have a battery.
Correct.
But I think there is the current limitation there, right? It's a voltage source as long as you don't exceed a certain current.
Certain current limit, right? That's right.
A practical voltage. But the ideal voltage source you're saying is?
That's right.
Any current in or out, the voltage difference is V.
That's right. So, in fact, normally when you look at circuit analysis problems, you do not have to think of a voltage of a current limitation.
Right.
Because this is an abstract concept of an ideal voltage source. Right. Of course, in practice what you are saying is right. There are lots of small non-idealities that we will probably learn in a later course.
Correct. Yes. Okay.
Okay. So, now this enforces a potential difference.
Yes.
Now, we know that in electrical circuits, there are two quantities of interest primarily, voltage and current. So, the minute you think of something that maintains a potential difference VAB, you can also think of a circuit or a circuit component rather. So, I will call this C and D. So, this is an ideal current source.
Okay.
And let us say its value is I. What this makes sure is that a current I is pulled from node D and pushed into node C. Irrespective of what you connect outside externally, there will always be a current from D to C flowing equal to I. And interestingly, the potential difference does not matter. So, now you think of an ideal current source, irrespective of what potential difference, the polarity, magnitude, etc., it can produce a current I.
Right. So, this is the exact dual of a voltage source.
It's the exact dual of a voltage source.
Wow. Okay.
Yes. So, in fact, the way it is normally taught is in terms of the VI characteristics. Right. So, in fact, if you draw the VI characteristics for these two components, you will find that, so let us say x axis V and y axis V and x axis I. So, maybe to make sure I will call this V naught and I naught.
Yes.
So, now if I want to plot V naught, what I am saying is that let us assume V naught is positive.
Yes.
For any current, the potential difference is always V naught. So, which means if I draw the VI characteristics for this device, it will look like this.
Yes.
It will just be a straight line parallel to the x axis intersecting at V naught.
So, we had looked at this earlier.
We had looked at this earlier.
And linearity and all that.
Right. Now, the same thing you can draw for a current I naught. Let us assume that I naught is positive. You can now show that irrespective of the voltage across it, the current is I naught. So, its VI characteristic should be parallel to the y axis intersecting the x axis at I naught. So, this is the characteristic for this, and for the voltage source, this is the characteristic.
Wow.
So, this is very easy to understand because what that says is you can have any voltage across the current source, the current will always be I naught.
Okay. So, for a voltage source, the current is determined by what you connect to A and B.
That's correct.
For a current source, the voltage is determined by what you connect. So,
that's correct.
Can we just look at a very simple example of connecting a resistor to the two sources?
Absolutely. So, if I were to take a voltage source V naught and connect a resistance R, let us say, and this was V naught.
Yes.
So, then of course, the potential difference across the resistor is V naught. Because of the battery. The battery maintains the same voltage. The current now is decided not by the battery but by the resistance that you have connected.
Correct.
So the way you would imagine this current IR is simply V naught by R.
Okay, so if I have a 1 volt source and a 1 kilo ohm resistance, I'll get a milliamp of current.
You'll get a milliamp of current.
If I have a 1 mega ohm resistance, I'll get a microamp of current.
That's right.
Okay.
That's right. And if you connect 1 ohm resistance, right, with 1 volt, you'll get 1 ampere.
1 ampere of current,
That's
right?
right.
Okay, so I can go orders of magnitude actually
That's
with
right.
ideal source.
With an ideal source.
Now what happens in a current source?
So in a current source, so let us say the current source is I naught.
Yeah.
I'm going to connect a resistance across this current source.
Yes.
Then let's say this resistance is R.
Yeah.
Then the current through the resistance has to be equal to R because
I naught.
I naught, sorry, current through the resistance R has to be equal to I naught.
Yeah.
And now the voltage developed across the resistance VR is simply decided by Ohm's law, which is I naught times R. And now again, if I take a 1 ampere current source, if I connect 1 ohm, the voltage is 1 volt. If I connect 1 kilo ohm, the voltage is 1000 volts,
1000 volts.
and so on.
Wow. Okay.
Okay.
So nice. So I think with this, sort of heads up, can we solve a couple of problems involving current sources?
Sure.
Okay. So let's start with a very interesting problem.
Okay.
There are only voltage and current sources in this problem.
Oh,
no
that's
resistors,
interesting.
No
Okay.
resistance.
Okay. Okay.
So there is a 6 volt vertically.
Vertically. Okay.
Positive on top.
Positive on top.
Okay. Then that's connected to a current source of 3 amps going top to bottom.
Oh, like across it?
Yes.
In shunt. Okay.
Shunt.
Like this top to bottom, right?
Yeah.
Okay.
Top to bottom.
Okay.
Okay. And then there is
what is the value of the current source?
3 amperes.
3 amperes.
Okay. So next there is a 12 volt source.
Okay.
That is connected negative to the top of the 3 amp.
Top of the 3 amp like this.
Yeah.
Okay. And it's 12 volts, right?
12 volts.
Okay.
Right. And then there is a 2 amp in the opposite direction as the 3 amperes.
I see. Okay.
Yeah. That's it.
Upwards.
Yes.
Oh, this is interesting. This
Okay.
is a nice problem. And 2 amperes, right?
And this is 2 amperes.
Okay. Excellent.
And it says, of course, you can use superposition to find the power absorbed. So what the problem is to find the power absorbed by the 6 volt source, the 3 ampere source, essentially all the sources. What is the power absorbed?
Power absorbed by
All
each
the sources.
source. By each
Each
source,
source.
right? Okay. Oh, this is interesting. Okay.
Okay.
Great. So I think the first thing we have to understand is we'll go back to this. The direction of the arrow is the reference direction.
Yeah.
If the current is positive, if I naught is positive, current is of course flowing from D to C.
Yeah.
If you have drawn the current source like this and current value is negative, it's flowing the other direction.
Other direction.
Positive current. So that is should be
Fine.
Straightforward.
Yeah.
We don't have that problem here because all the current sources are all positive.
Positive, right? Yeah.
Okay. So now what we'll do, we can approach this in many ways.
Yes.
In fact, you can just use the primary VI characteristic
Yes.
of each device
Yes.
and to solve this problem.
Yeah.
So maybe we'll do that method first.
First.
And then after that, we will also see if superposition can be used.
Can be used,
Because
exactly.
you can. Superposition is always useful.
Correct. Yeah.
Okay. So maybe we'll solve it first by finding out different currents and voltages.
Yes.
So the first thing I would say
So
is
why don't we start with the 12 volt source?
with the 12 volt source. So the 12 volt source has we need to find out the current through the 12 volt source.
Yes.
So I see that it is in series with the 2 ampere current source.
Yes.
So clearly the current through the 12 volt source has to be 2 amperes.
Has to be 2 amperes.
Has to be 2 amperes because there is now no other path for the current
for the
to
2
flow.
ampere current. Yeah.
And our general assumption for any unknown two terminal element, so between x and y, this is some unknown element. If the current is entering, positive current is entering and the voltage is positive voltage is like this, power absorbed
Is V
into I.
I.
Okay, this is our general convention.
Otherwise, you are saying if the current is in opposite direction, power is delivered.
Power is delivered.
Yes.
If the power absorbed comes out to be negative, then it is power delivery.
Correct.
Right.
Yeah.
So for example, let us go back to this. So for the resistance R, so current is flowing in this direction.
Yeah.
the voltage is in this direction.
Yes.
So the resistor is absorbing power,
Yeah.
converting it electrical power, converting it into heat.
Heat.
If you look at the voltage source, the direction of current is opposite. It's coming out of that element.
Yeah.
So it is delivering power. The power absorbed is a negative number.
Correct.
Okay.
Got it.
So we will follow that convention.
Yes.
And let's start with this 12 volt source.
Yes.
So I can see that current is entering the positive terminal of the 12 volt source. So the power absorbed for the 12 volt is 12 into 2.
12 into 2, that is V into I.
V into I, which is 24 watts.
So
this is positive. In fact, this shows that the 12 volt source is indeed absorbing power.
Yeah, absolutely.
Okay.
Great.
So then I want to look at
let's say the 6 volt source.
6 volt source. Okay. So now I want to see 6 volt source.
Yeah.
So of course I am going to take this as the
Direction
because I want to find out
absorbed.
So I'll call that some I6. Easy.
Yeah.
Okay. Because it's for the 6 volt.
Yes.
I find this out by performing KCL at this node.
Yeah.
Okay.
Yes.
I have I will write it here.
Yeah.
So the total current entering the node is 2 amperes.
Yeah. It's 2 amperes.
From the right side.
Yes.
That has to be equal to the total current leaving.
Yes.
So which is 3 amperes, plus I6.
Plus I6.
In our convention.
Absolutely.
Okay.
Yes.
So
correct.
From this we see that I6 is actually minus 1 ampere.
Yeah.
Okay. This tells me that the power absorbed by the 6 volts is going to be 6 into minus 1.
Yeah.
Which is minus 6 watts.
In
In other words, that 6 volt battery is actually delivering
power.
It's actually delivering 6 watts of power,
It is delivering
absorbing minus 6 watts of power.
minus 6 watts of power.
Okay. So now let us do it for the 3 ampere.
Current source.
For which current source do you want to do it?
Let's start with the 3 amperes.
Let's start with the 3 ampere. So again, I see that, remember my convention, it should be entering the positive terminal, leaving the negative terminal. So the first thing I will note is that for this current source, current is of course flowing in this direction.
Yeah.
I will take my, I will call this V3
Yeah.
for the 3 ampere.
Yes.
And I can see that the 6 volt source is coming directly across the 3 ampere.
Yes.
So I can also say that V3 is plus 6 volts.
Plus 6 volts. This is
So
yes.
and so current is entering the plus terminal as well.
Correct.
So this absorbed by the 3 ampere is clearly 6 times 3,
18
which is plus 18 watts.
plus 18 watts. So the 3 ampere source is also absorbing power.
Is absorbing power.
Okay.
Okay. And by the way, I don't need to do anything else. I could just use power conservation because I have only voltage sources and current sources. I know that the sum of all power absorbed should be 0.
0.
I
Okay.
could actually do it that way as well. This is
so-
third method.
Okay, right.
Okay. So I could just say 24 plus 18 is 42.
Yes.
Minus 6 is
36.
36. Minus 36 watts
Is
should
what?
be the power absorbed by the 2 ampere current source.
Okay.
I could do it that way.
Let's check.
Let us check. So my guess,
Guess.
okay,
Power absorbed.
by the 2 ampere is going to be 24, so minus of 24 plus 18 minus 6.
Yeah.
So this is minus 36.
Minus 36 watts.
Minus 36 watts.
Excellent. Yeah.
Right? This is my guess because I have voltage sources, current sources. If something is producing power, something has to absorb the
Absorb power. Yes.
Okay, that is
Good.
my guess.
Great.
Let us calculate it in the regular way.
Yeah.
So we are doing for the 2 ampere current source,
Yes.
and so I need to find out the voltage across the 2 amperes.
Yes.
And current is coming in this way,
Yeah.
entering here. So I need to find out the voltage in this direction.
Yes.
So I'll call that V2.
V2. Yeah.
Okay. So I need to find out the voltage drop going from node A to node B.
Yeah.
Okay. I can actually traverse this path which only has voltage sources,
Correct.
and so VAB is basically in this, with this convention,
Yeah.
is actually I want the drop, but I can see that I have an 6 volts and then 18 volt increase.
Yes.
So this is basically minus 18 volts.
Volt. Yeah.
So this is minus 18 times 2 amperes,
2 amperes.
which is minus 36
Watts.
In fact, my guess is correct.
Exactly, right.
Great.
Okay, so this is sort of very nice, right? And I mean, like you mentioned, I'm sure we could also use, maybe let's just look at one source and see how we can use superposition to get the same answer.
Absolutely. So maybe we'll try the 6 volt source.
6 volt source.
6 volt source. So we want to find out the power absorbed by the 6 volt source.
Yeah.
So maybe we'll use superposition to find that out.
Yes.
I'll make a copy of this. Okay. So okay, so we'll get rid of all these variables for now. Okay. So we are going to use superposition to find out what the voltage is across the, what the power is across the 6 volts.
Yes.
To do that, I need to find out this current I6.
Yes.
Okay.
Yeah.
So I'll have 3 cases. I will take the 3 ampere current source, 2 ampere current source, and 12 volt current source one by one.
Okay.
I will find out I6 in each case.
Yeah.
Add all of them. That will give me I6.
Yeah.
Right.
Okay.
So let us take the case of the 3 ampere current source.
Yes.
So first step. So only 3 amperes.
Yes.
Okay. Only 3 ampere source.
Yeah.
Now we need to figure out what we saw, in the previous class, that if you had a current source, you de-energize it, the voltage goes to 0, which means it's a short circuit.
Yeah.
So if you have a voltage, de-energization makes it a short circuit.
Yes.
If you have a current source of value I, if you need to de-energize, that means there is no current.
No current.
So it needs to become an open circuit.
Open circuit. Yes.
Okay. So we need to remember this.
Yes.
So if you want to remove the 12 volt source, you are going to short circuit. But if you remove the 2 ampere source, you are going to open circuit. So your circuit will now become like this. So you have this 3 ampere source.
Yeah.
But you will have a short circuit here
and then
an open circuit here.
Okay. Right.
Okay. And this is I61.
Yeah.
And this is 6 volts.
Yes.
So this is a 3 ampere current source.
Yeah.
This tells us that
I61 is minus 3 amps.
Minus 3 amperes.
Okay.
Same way, I am going to do B, which is only, shall we say only 2 amperes?
Only 2 amps. Yeah.
Only 2 amperes. So in which case 3 ampere will become open circuit.
Open circuit.
So
I have 6 volts.
So I'll have this open circuit here.
Yeah.
And then 12 volts is short circuited. I only have the 2 ampere current.
Amperes. Yeah. Perfect.
2 amperes. And this is I62.
Yeah.
So I62 is clearly 2 amperes.
Yes. I62 is 2 amperes.
2 amperes. Now I need to do the third case, which is only the 12 volts. Okay.
So you have to open circuit the 3 amp and the 2 amp.
And the 2 amp. Okay. So first I'll draw the 6 volt source.
Yeah.
I'm going to open circuit the 3 ampere.
Correct.
So nothing connected. And I have my 12 volt source. But now I'm also going to open circuit the 2 amperes.
Okay.
So this is 12 volts. Well, because there is no path for the current to flow, I63 is 0.
I63 is 0. Okay.
Okay. So which means
the I6.
I6 is just the sum of the 3
currents.
So this is basically minus 3 amperes plus 2 amperes minus 1 ampere.
Yes.
Let us see what we got earlier. We got minus 1.
Minus 1 ampere.
So where did we, I6 is minus 1
minus 1 ampere. Yeah.
So right. So this makes sense. So which means P absorbed is basically is minus 6 watts.
Is P absorbed? Yeah.
By the 6 volts, right? So P absorbed by the 6 volts is basically I6 times 6 volts.
Correct. Yes, minus 6.
Minus 6
watts.
Same as before.
Same as before. Okay, great. So we could do the same thing now for
correct. So clearly superposition works as long as even if you take the absorbing or element as a voltage source or a current source, you can take all the other voltage or current sources and apply them one by one.
One by one.
To find out the
great.
current or
Okay.
voltage.
Right. Nice. Okay. So, okay, let's try, another problem now involving resistors as well.
Okay.
Okay. So, I think this is sort of something we saw. So, let me start with a familiar problem. Okay. So, you just draw like maybe a 12 volt source.
A 12 volt source.
Positive on top.
Positive on top.
Okay. A shunt 60 ohm resistor.
A shunt 60 ohm resistor. Okay.
A shunt 8 ohm in series with plus 24 volt.
Okay. So 8 ohms and a plus with the top one
Yes,
on top?
yes,
Okay.
24 volt.
So 24 volts, and what is this value of the resistor?
8 ohms.
8 ohms, okay.
Okay, and finally you have a shunt 40 ohm resistor.
Okay.
Okay, so let me see. Problem 22 by making for each of these replace the network. Okay, let's say we want to find the voltage across the 40 ohm.
Okay. Oh, this is easy.
Okay.
Because the voltage across the 40 ohm
is getting set by the
getting set by the 12 volt source.
12 volt. Okay, so
Right.
this is sort of
This is kind of, I go through this loop.
Yeah.
This is a very simple problem.
Yeah, and even if we had, let's say, another voltage source with the 40 ohm, I think this is something we did in the earlier class.
did in the
This is
earlier
easy.
case.
Now I want to replace the 12 volt
Uh-huh.
with a 2 amp current source.
Okay, so this is the next example.
Yes.